This previous year question, when translated into figure, it appears like this. A cell of 3 volt EMF, 0.2 ohm internal resistance, another cell of 6 volt EMF and 0.4 ohm internal resistance is connected. They are connected in parallel and the combination is connected across a 4 ohm external resistance. Now this is the conventional way of writing, but here for the solution purpose, since we have to solve the equivalent internal resistance, the current drawn from the combination, and also the EMF of the equivalent cell or equivalent battery. So I am going to redraw this figure here, and it has been drawn. So look at this figure first. The 3 volt cell and the internal resistance 0.2 ohm. I have shown the EMF and internal resistance separately. Similarly, for the 6 volt, the internal resistance is written separately, and the 4 ohm resistance, which is the external resistance, is as usual here. Now, the first thing we do is to use the junction rule, Kirchhoff's current law, or node rule. All the three, any of these three names is used for the same law, which is called Kirchhoff's current law, node rule and junction rule. What does it say? It says that the currents entering into a node, the algebraic sum of the currents entering and leaving, it should give you 0. Exact statement is algebraic sum of the currents into a node is 0. Now when we are saying algebraic sum, that means the current going in, if given positive sign, current going out must be given negative sign. Let's see. So I1 and I2, they are going in, so they are plus I1 and plus I2. I3 is coming out from the junction, so it is minus I3. Now remember, before this, why did we take the direction of current as I1? I say there is no reason for it. You could have taken even the opposite direction. Doesn't matter. Algebra will give us the actual direction. And in the due course of solution, you will understand how algebra helps us to find out the correct direction. So whatever you wish, take the direction of current according to your choice. So here it has been chosen I1 and I2, and this is I3. So the sum of I1 and I2 must be equal to I3. What is this equation tells us? In fact, we have taken the algebraic sum, means keeping positive sign for current going in, I1 and I2 are positive, but current going out from the node B is given negative sign, so I3 is negative. Now, another rule that we are going to use is Kirchhoff's voltage law. Kirchhoff's voltage law is basically the law of conservation of energy. In fact, we go around in a loop to account for the fall and rise of potential. So when we have to write Kirchhoff's voltage law, which is written as algebraic sum of all the EMFs and all the potential drops in a circuit is 0. When we have to apply Kirchhoff's voltage law, the best approach is that we write the voltages just close to the resistances about which we are talking. Let us say in this branch the current is I1. So the potential drop across 0.2 ohm resistance would be I1 into 0.2. As you know, potential drop is I into R. So it is I1 into 0.2 or 0.2 I1. Similarly, across 0.4 ohm, the potential drop is 0.4 I2. Across 4 ohm, it is potential drop is 4 I3, or the change of potential is 4 I3. Now, KVL in loop F, A, B, C, D, E, F. Obviously, the first thing we should do is to name the corners. So, A, B, C, D, E, F, the corners have been named so that we can refer to the loop that we are talking about. So, the first loop we are talking about is the bigger loop. You can notice here there are 3 loops, the bigger loop and these 2 smaller loops. So, there are in all 3 loops. We are considering the bigger loop. Which loop? F, A, B, C, D, E, F. So, we started from F, ended at F. So, in going from here to here, first thing we notice, we are going in the direction, same direction as the current. But remember, current flows from higher potential to lower potential. Higher potential to lower potential. That means we are going down by 0.2 I1. So, down will be represented as minus. So, minus 0.2 I1. When we have crossed this component, we have gone down by minus 0.2 I1. And in going from here to here, actually we are going from negative of the battery to the positive of the battery. Now, negative terminal represents lower potential, positive represents higher. So, in this case, we are going from lower to higher. So, plus 3 volt. Now, this does not have any component. Here is the component. But through this component, the current is in this direction. And we are going in the same direction as the current. So, we are going from higher towards lower. So, we are going down. So, that is minus 4 I3. So, here is minus 4 I3. So, this becomes equation number 2. Equation number 1 we have already seen. Equation number 2 is here. Now, there are 3 variables in this whole process. Look, I1, I3 and I2. So, 3 variables. To solve their values, to get their values, we need at least 3 simultaneous equations. But by now, we have only 2, equation 1 and equation 2. So, we set up or we find another equation, and that comes from Kirchhoff's voltage law in loop F, A, B, E, F. KVL in loop F, A, B, E, F. So, again starting from here to here, we are going down by 0.2 I1. So, minus 0.2 I1. Here to here it is plus 3. In going from here to here, look, current is in this, in going from here to here, we are simply going from positive of the battery to the negative of the battery. So, we are going from higher to lower potential. How many volt? 6 volt lower. So, it is minus 6 in going from here to here. Now, in crossing the resistance, since the current is coming from this direction and we are crossing in this direction, means we are going from lower to higher. So, it is plus. So, plus 0.4 I2. So, here it is plus 0.4 I2. So, that forms our equation number 3. Now, this equation number 3, I am going to simplify it. Look, on simplification, this plus 3 minus 6 gives you minus 3. This is again 0.2 I1 and 0.4 I2. So, one way to make it look better in whole numbers is to multiply it with 10. Once we multiply, we get minus 2 I1 minus 30 plus 4 I2. Further, we notice 2 is the common factor. So we divide the entire equation by 2 and therefore we get minus I1 plus 2I2 minus 15 equal to 0. So this is the same equation 3 now put in a compact form and a whole number coefficient form. So the same equation 3 is rewritten, so its name is 3a, and this is a good way to write. Now let's get on to the next aspect. In equation number 2, look, there is current I3. We want to eliminate I3 simply because I1 and I2, only two variables we want to keep overall. So here it is I1 and I2. So in this equation also I want it I1 and I2. So in equation 2 I put the value of I3 as I1 plus I2. I3 is I1 plus I2. So in equation 2 we have put here, look, equation 2 is rewritten here, minus 0.2 I1 plus 3 minus 4 and I1 plus I2. So further you do the algebra, and in the process, look, minus 0.2 I1 minus 4 I1, that makes it minus 4.2 I1. Then this is minus 4 I2 and plus 3 equal to 0. Now again same, we have multiplied it with 10 throughout. So this becomes 42, this becomes 40 and this becomes 30. And again we have a common factor 2, so divide by 2 throughout. This equation actually becomes minus 21 I1, this becomes minus 20 I2 and this becomes 15. Now look at equation number 3a. In fact, this equation number 2 has been rewritten in this form, so its name is 2a. So look at now or focus on equation number 2a and 3a. Now if you look at equation number 2a, there is minus 21 I1 minus 20 I2 and here it is 2 I2. So to make it 20 I2, we multiply this entire equation by 10 and write it just under it. So that becomes minus 10 I1, 20 I2 plus 20 I2 and minus 150 equal to 0. So having obtained this equation below it, now we can easily notice this is minus 20 I2 which can cancel with plus 20 I2. So when we add them together, we are adding these two equations together. When we add them together, I2 gets cancelled. You are left with 31 I1 and here it is minus 135. So I1 is minus 135 upon 31 ampere. So I1 is now known to us. So to find out I2, we are using equation 3a again. So I1 is minus 135 I1. Minus 135 by 31. So I1 is minus 135 by 31. Then this is 2 I2 minus 15 equal to 0. So this, when taken to the other side, becomes minus 135 by 31 and this is just 15. And this 2 is on the other side to divide. So 465 minus 135. that is 330 by 2 into 31. On cancellation, you get 165 by 31 ampere. So now the situation is that we know we know current I1 and we know current I2. As I said in the beginning, the value of current I1 has come out to be negative. It means the direction of current that we have chosen, actual current is just opposite to it. The value of current I2 is positive. It means whatever direction we have chosen initially, same is the direction for I2. Okay. So let's now calculate I3, because I3 is what? I1 plus I2. So I1 comes from here and I2 comes from here. We take the LCM, add it up, it comes out to be 30 by 31 ampere. It comes out to be 30 by 31 ampere. So that is I3. So our initial circuit, what's the new picture? Just have a look. The new picture is that the two cells whose internal resistance is 0.2 ohm and 0.4 ohm are connected to a 4 ohm external resistance. Now I3 is the current which we know. Now the two internal resistances are known to us. In this circuit, if you look at, these two internal resistances are in parallel. So the net internal resistance would be 1 by R equal to 1 by 0.2 plus 1.0.4. This 0.4 is the LCM. Here you get 2 plus 1, that is 3 by 0.4. Or you can say 30 by 4 or 15 by 2. So R is 2 by 15 ohm. So now we know the internal resistance of the equivalent cell. Internal resistance of the equivalent cell. We don't know the EMF of the equivalent cell, but rest of the things we know. So these two cells are represented by a single cell whose whose EMF is E and internal resistance is 2 by 15 ohm. Current I3, it is 30 by 31 and external resistance is 4 ohm. So that entire circuit has been now simplified to this single cell having some internal resistance, sending some current I3 in the circuit. So how do we find out E? Again, Kirchhoff's voltage law comes to our rescue. Look, we are applying KVL again in this direction. So here there is a drop or a change of potential as current into resistance, I3 into R. So applying KVL, in going from here to here, we are going in the same direction as the current. So high to low. So minus I3R. From here to here it is plus E. From here to here it is minus 4I3 equal to 0. So EMF is 4I3 plus I3R. I3 is again common. I3 is outside. It is I3 into 4 plus R. Let's substitute all the values. Now I3 is 30 by 31. Here it is 4 and it is 2 by 15. You take the LCM, it comes out to be 62 by 15 and this comes out to be 30 by 31. Now 15 2s are 30 and 31 2s are 62. So 2 2s are 4. So 4 volt is the EMF. So now we know everything about the circuit. Firstly, while you are solving a question in physics, you should read the question at least 3 times. The first time to get an initial introduction, the second time for solution and third time for checking it. So once you check, in this case, you will find that you have answered everything. The equivalent EMF was asked, it is 4 volt. Internal resistance was asked, it was 2 by 5 ohm. The current through 4 ohm resistance was asked. It is 30 by 31 ampere. So everything answered. Thank you.